Test. Okay, thanks for the introduction. I'm Xiaoyi Lu from The Ohio State University. So today I'm going to give another talk about how to build efficient cloud with SR-IOV-enabled InfiniBand networks. So these days, many people are trying to move HPC workloads on top of cloud. So now the question is, nobody wants to use a low-performance cloud, right? Everybody wants to use a high-performance cloud. So now the question is how to build the efficient HPC cloud. So if you look at the hardware perspective, a lot of advanced features and chips or devices you can build and install in your cloud. Let's say multiple accelerators, a lot of memories, SSD, NVMe SSD, NVRAM, and also RDMA-enabled networks with SR-IOV support. Now, the key of this talk is actually centered around SR-IOV mechanism. So basically for SR-IOV, if some of you are not familiar, so it's very simple. It's basically like a hardware virtualization. It can represent the PCI device as a multiple virtual function. And then each of these virtual function or virtual device can be assigned to each virtual machine, like a guest domain, so that this guest domain will use the existing driver, whatever you have, and then run on top of the virtual function, just like in a dedicated manner. So this will work with both InfiniBand and high-speed Ethernet. It's very fast. Later on, I will show some numbers. Now the question is, what kind of board challenges, even you have this type of newer network features and hardware support? Now here we just list some of them. The red ones is something I want to cover in this talk. For example, how to support both virtual machines and also as well as containers. And then something like SR-IOV, IOV, IPC, CMA, those kind of mechanisms we also want to introduce and how to utilize them. And the key actually we want to present here is how to achieve locality-aware communication inside the cloud environment. And something like NUMA-aware communication for nested virtualization and the migration support under SR-IOV environment, as well as some other perspectives. Now this is the outline of the approaches our team actually trying to explore. There are multiple different ways, different topics I want to introduce here. The first one is MVAPICH package with SR-IOV and IOV. So MVAPICH has been in the community for more than 16 years. So a lot of clusters, including the #1 in the world, is trying to use MVAPICH currently. So, but for the cloud perspective, the MVAPICH package actually is still new baby. So only like 2 years old. But we have done a lot of work. Let me introduce what we have done in this picture first. So as you see that there are two domains. One is guest 1, one is guest 2. They are running on top of one hypervisor, okay? So once you have SR-IOV, you can have multiple virtual functions in this cluster, in this node, and then you assign this virtual function to guest 1, this virtual function to guest 2, okay? Now, you can run default MPI without any problem because this hardware virtualization, you don't have to change anything in your software layer. So that you can run your default flow, MPI flow, in this virtual function and communicate. But this is not a high performance, but this is not the only high performance path you can use. There's another mechanism called IOV, which means inter-VM shared memory. So in today's talk, right, many providers, many library have a modular, like has shared memory support. Similarly for hypervisor, there's a different kind of way to do inter-VM shared memory-based communication. So that another question is how MPI know this channel is available and how you know whether this rank and that rank can use shared memory or not. So that thing is what we call the locality-aware communication, so that we are able to detect where in the runtime the rank location in the VM, and then we can dynamically select the best path for your MPI communication. So this can run with standalone manner. We actually also did some support in the OpenStack, so that when you use OpenStack Nova to deploy your virtual machines, you just need to say that I want IOV support. We automatically set up the IOV channel for your virtual machine, so that then when you run your MPI jobs in the cloud, the MPI library will automatically detect whether IOV device is available or not. Based on that, it will select the path dynamically. So with this support, if you take a look at the application numbers, so here the green one is like I said, use default SR-IOV, default MPI, no any changes. It runs, but performance is like this, the green one. Is the one like the gray one is the native without any virtualization. Okay, just run the MVAPICH with native environment, you get this much performance. So sometimes there's a big gap, but with our optimized design, you are able to reduce this gap to less than 10% overhead. That's the message. So now this is about performance. We know SRV is good. With some help from locality-aware communication, you get better performance. That's good. But now the question is, when you move SRV or you use SRV in your cloud environment, there's one major blocker is live migration, okay? So far, SRV cannot support live migration. Let me give you a picture like this. So this KVM, you have a Mailbox card, and then you assign a virtual function in the virtual machine, and then you run command like, I want to do a live migration. Then the KVM will tell you, no, we cannot do that because there's some device doesn't support that, okay? So this is the current status. So in the field, of course, there are a lot of people trying to propose different solutions in different layers. So for example, I can change driver, I can change operating system, change hypervisor. Whatever you do, you always need to change something in your software stack, critical path to do this kind of support. Now the question is not that. The question is, can we don't change anything in operating system, in driver, so that you don't have to make your solution bound into any vendor solutions or any version of operating system and hypervisors. We want to do this in API library, in user level, so that we can support any kind of SRV devices, potentially. So that's what we did. So there's basically in MVAPICH 2, in order to support this live migration, we have two major components. One is the extra controller, which is trying to get your migration commands and the signals, and then transfer these signals into the virtual machines, so that when your MPI jobs running, you're able to detect this signal, and then you're able to suspend your connection and dry out your on-the-fly messages, and then you can hot unplug your device, so that live migration is doable. Okay. So with that, let's take a look at some of these numbers. With live migration, the major bottleneck actually is the speed of your network, because you have to transfer your dirty pages during the live migration phase, right? So of course, if you use high performance protocols like RDMA, which can give you much better migration performance, like this graph shows. Okay, it can reduce migration time by 20%. This is a 512 megabyte virtual machine memory. And then another thing I want to highlight is that with our container, we are able to do the parallel migration. So you don't have to migrate virtual machine one by one. We can migrate the virtual machines in parallel, which can also reduce the time like half. So that's the migration time. But many people say whether you influence application performance or not. Of course. So during the migration time, you still have a very short, like a duration of shut down your communication, right? So this benchmark show a big jump here. This means basically when this benchmark do the 4K message transfer, we trigger the migration. And then during that time, the time will get increased, of course, because at that time we have to do a lot of things in the NPM library. And this benchmark is only like a communication intensive benchmark. There's no any computation. So there's no any way you can do overlapping, because your communication needs to be suspended, right? So that's why you see a big jump. But in the real application, things can much better, okay? Because in real application, you have a lot of time which actually doing computation, not fully communication. So as long as your application is doing computation, we are able to overlap the live migration phase with your computation phase, okay? There's only fairly short duration, which if you go into the MPI library, we give you some like a microsecond level or millisecond level suspend, and then we just go. So that's why in application, if you run applications, you see that NM means basically there's no migration, okay? So we can almost similar to the no migration case from the Llama perspective. So this is about what we did for the virtual machine to bring SRV, as well as support live migration in SRV environment. Now the next thing is many people trying to say that, okay, now because container is so lightweight, why you want to run your jobs in the virtual machine, right? Why we cannot run in the container? Of course, you can run container. So the major difference between container environment and the virtual machine environment is that in container environment, you don't have a hypervisor, okay? And so that in the container, you just need the dependency libraries and then your binary so that you can run. That's much lightweight than this side. This is the hypervisor side, okay? So this is also why people try to use containers for HPC. Now the question is, in container environment, is there any challenges to get the near native performance? The answer is yes. So for example, let's say Docker. In Docker, right, by default, they're going to isolate something, okay? For example, they isolate your namespace. So that in Docker, instance A and Docker instance B. Even they're in the same node, you still don't know, okay, there's another rank in another Docker which run in the same node. So in that case, still a lot of MPI level optimization cannot be triggered. For example, kernel-based copy, CMA, right? Or some kind of shared memory-based computation also cannot be triggered. So in this way, we have to detect, again, your rank location based on the rank distribution. After we detect that, we are able to select the best path, like either CMA or shared memory or HCA, dynamically. So that's the key. With that, let's take a look at some of these numbers. Again, if you look at this graph 500, this green bar is the default MPI. You run with default Docker. With one process, okay, it's fine. One Docker per node is fine. You get a similar performance as a native. But when you increase number of Dockers per node, you see significant performance degradation in Docker environment. So with our design, we are able to reduce the overhead around 70%. So this is about Docker. Because now let's see Singularity. Because Docker was not designed for HPC. Singularity, when you get born, it has MPI in mind. So for Singularity, it has by default, has a lot of setting choice, which very friendly to MPI workloads. So we run these Singularity tests under the Haswell as well as KNL. We see very good performance, okay, very similar between Singularity and the native, almost less than 7% performance differences. That is for the benchmark, and then for applications, similarly, we have 7%. We only see around 7% differences for NAS as well as Graph 500. Now, another story is that, okay, so some people want to use container. For example, I want to package, especially when I do development. I want to package my dependencies and my binary in one instance or in one image, and then I just do a Git, like a Docker push to the Docker Hub, right? So and then give some link saying that, okay, you want to use my application, please do the Docker pull, so you get my application. So this is how you develop your applications in the real scenario. But sometimes when you run your application in the cloud, so the provider gives you virtual machines, right? So in that case, basically means what? This basically means you actually will run your application in a Docker environment, but underneath is virtual machine. We call this a nested virtualization. You have two layers of virtualization. One is Docker layer, one is the virtual machine layer, okay? So this is the example we showed here. Now, under this environment, how many communication paths you have? Actually, there's a lot. For example, if your rank is in this container, which may be in this socket, so you may have like inter-socket, inter-container communication. And then for this guy, you may need to go to inter-socket communication, but it also inter-container and also inter-VM. Similarly, you may across nodes. A lot of paths available. So now this also brings some challenges into MPI library. Because for your MPI library, you have to detect all these topologies so that you are able to efficiently and dynamically select the best paths during the application runtime. So with this, we develop some kind of component in our MVAPICH library. So we are able to detect your VM locality, container locality, and then also NUMA information, so that we are able to do two-layer NUMA-aware and the locality-aware communication coordination. So that's the key. So with this, let's take a look at some of these numbers again. So like I mentioned earlier, either for Docker design or for the KVM design, we only do one layer locality detection. With this, we see that one layer is not performing the best. For example, for bandwidth, the one layer is only here. But with our two-layer design, we are able to get much better performance, like 84% improvement, something like that. That was for inter-socket. Now for inter-socket communication, similarly, we are able to get 42 and 25% improvement. And then for application, similarly, we are very close to our design, two-layer design can give you the best performance as well for Graph 500 and LAS. Okay, so this is about the designs in the MPI library. But in the meantime, people are also trying to say that how about we also design with some other cloud orchestrators, like either SLURM or OpenStack. I have shown some story about OpenStack. For SLURM, similarly, we did something like how to extend SLURM to manage virtual machines deployment. For example, when you submit a job, you just let me know what kind of virtual machine configuration you want and how many virtual machines you want to deploy in your application. So with that, we actually propose some SPANK plugin, like we call SLURM V. So basically, this plugin, what we did is kind of pass your configuration requirements, and then we dynamically deploy virtual machines when you allocate the nodes, and then run your jobs over there, and after that, tear down the resource and get everything back. Okay, here the major idea is that I have to set up the virtual machine in the best manner so that I'm able to get all the channels I need in the MPN library. So that's something we did for SLURM plugin, but we also think whether we can combine both SLURM and the OpenStack, because many things has been done in the OpenStack community. So that can we offload some of this logic to the OpenStack daemon? So OpenStack daemon can actually deploy virtual machine for me and then call back, or we get some signals and get done so that I have a virtual machine now. I can run my MPI jobs in the virtual machines. So this is something we did how to run OpenStack and SLURM together. So in OpenStack, there's some mechanism called like a whitelist as well as PCI whitelist, so that we can pass through the SRV driver to the SRV device to the virtual machine. So that's something I want to highlight here also. So with this, actually, we did some very interesting performance comparison here. So basically in the cloud environment, sometimes your resource may have different sharing pattern. So you may get some physical nodes, but when you run your virtual machines, your virtual machine may run together with some other user's virtual machine, right? So there's a different way of sharing your resources, and the resource sharing is the key of cloud. So we actually summarized 3 different kinds of sharing pattern in the cloud. We call it like exclusive allocation, where you run sequential job. This is the simplest one. Or you have shared host allocation, but you do run concurrent jobs. Or you have exclusive allocations, shared host allocations, also concurrent jobs. So we run, in this case, for concurrent jobs, we run 2 jobs. One is NAS, one is Graph 100. We run together on the same environment. We want to see how much contention and whether everything can be isolated properly. With that, actually, we see very good performance here. We only see like 4% overhead, something like that. Okay, so all those things are like we run MPA in the cloud environment. We run with some kind of standard benchmark. Now the question is, can we run with some real applications in the cloud? So during last year, so we have been working with a lot of neuroscience scientists in their environment or in their community. The key is what? For example, some scientists, they want to analyze your brain activities. Okay, I don't understand what they're going to do, but the key is that easy and fast discovery, science discovery. That's the key. If you look at HPC cloud side, the key is what? The key is easy to use and high performance. So actually, this can be matched together. So they only need our technology. We only need to help them to get performance and easy to deploy, easy to run. That's how we can work together. So there's one case study we did with some Indiana University neuroscientists. They have a program called Life. So like I said, it's going to get your MRI images and then analyze what's going on in your brain. So earlier it was just running in one node. They have tried some multi-threading, but it's not they could not get a good performance. So we work with them. We develop some MPI-based Life design for them. We can highly optimize their code. This is the details. So let's show some numbers here. So we run their sequential version and our version on StackTMP, on single node as well as multiple nodes later. So we see very good performance improvement, like 8.7x speed up. They are very happy with this. Now the question is how we move these things to cloud. So in order to further help them, we make this MPI Live, including all the dependencies. They're actually based on some MATLAB code, okay? A lot of dependencies. So we're trying to help them packaging everything in a Docker version. So we have Docker containerized version, which is available in this URL. This is a new project, NeuroHPC, which launched by us. So we are going to help them to run their NeuroHPC jobs on top of cloud efficiently, okay? Because sometimes even for them, they're hard to deploy all these dependencies in the cloud. So we are trying to help them just do a Docker pull, run our MVAPICH version, and you get a near native performance. That's the key. So like here, we run some native performance in one container and 2 container case. We see almost the same performance. There's no difference. So in this way, we are able to help a whole domain. Look, you use our solution, you are able to deploy everything very easily, just one command, and you get near native performance. This is how cloud should work. We believe that. So this is some story from HPC side. We also did a lot of things in the big data area, right? So we are trying to show some case studies here as well, how you can move data analytics jobs and begin some kind of data applications on top of the cloud environment to get good performance. Like I mentioned yesterday, there's a lot of packages available in our HPC project. So the one thing I want to highlight here is that maybe today or tomorrow we are making a new release in Hadoop package, which will support Singularity and Docker for RDMA Hadoop, which will give you, again, near-native performance. So, but for RDMA Hadoop, the native environment design, I think I introduced earlier, yesterday, I think. So now the question is, when you run in the cloud, what we can do, okay? So for some of you may not be familiar with Hadoop, let me give you a breakdown on the architecture, okay? So for Hadoop, there are multiple components which you have to keep in mind whether you can optimize for cloud environment. Of course, HDFS is very important. Look, if you deploy HDFS in cloud, right, your data node data node process may be in the virtual machine. Earlier, the philosophy of HDFS fault tolerance is what? I put one replica in one node, second replica in the node, but in the same rack, in another node, but in the same rack. And the third one, I go to another rack, so that no matter node failure or rack failure, you still have some replica in your cluster. But once you have virtual machine layer, this topology gets changed. How you know I'm still in the one physical node or not? Whether I'm in the same rack or not. So those things needs to be detected. Okay, that topology needs to be detected. And once that things get detected, HDFS block placement policy needs to be changed. This is one thing. Second thing, even for Yarn. Yarn is going to schedule your container, where to launch your container. Again, related with topology. You don't want to launch a lot of containers in the same node so that, look, this node becomes very like a resource contention, but the other node is idle. You don't want that, right? Similarly, for Yarn component, you also have to be extended. For MapReduce, same thing. So we actually did some of this design. We call RDMA-Hadoop-Virt. We actually enhance both Hadoop Common, MapReduce, Yarn, and HDFS, all these layers. Okay, there's a paper in CloudCon. We present this over there. Now let's take a look at some of these numbers. We run Cloud Burst application, a self-join from HighBench, I think. Self-join in HighBench or something. We are able to reduce the execution time in the cloud environment by 30% to 55%. Okay. So some people say when we bring virtualization, right, there's a lot of overhead, especially when you have a lot of I/O. Of course, yes. So with some advanced design, you probably can get much better performance without changing any hardware and your application. So that's about Hadoop. So earlier talk, whatever Intel presenter mentioned is Ceph, okay, in OpenStack. So there's another OpenStack component is also object storage called Swift. It's very useful. It's like S3 service, open source S3 implementation. So this is the Swift architecture. So you have object server, and then you have a proxy server. Proxy server is actually sitting in the your security. Because of firewall, those kind of things, you need some proxy server to get all collections and all the requests, and then you will distribute those requests back to the back end object storage servers. So this is the architecture of Swift, and they support both put and get operations. So once you trying to storage some object in the Swift, you need to do put, or when you want to get it back, you do Swift get. Okay. So of course, there's a lot of communication operation happening here. So by default, Swift is using TCP protocol. So now the question is, are we able to redesign Swift to take advantage of RDMA? This is one thing. Second thing is, except communication, what kind of other bottlenecks are there in the Swift? Okay. So we actually proposed two designs. One is you don't have to change anything in client, because the client will talk to proxy server here. So if you change something here, then your application may need to get changed yourself. For example, at least you need to link with your new Swift client, right? So we don't want to do that, because many of this traffic may happen in the wide area network because of like this cloud, okay? But this path, like the red one, this actually may be in the same cluster, right? This path can be easily get optimized by RDMA. This is one thing we did. But second scenario is this. We also think some case you probably have some flow which talk to proxy server, but actually inside your cluster, not outside your data center, okay? In that case, security may not be the big concern. So in that case, can we bypass by proxy server? If you can, because for this architecture, proxy server always become bottleneck because all the traffic come to proxy server and then dispatch to the backend and then come back. So if security no longer is a concern inside data center, so you have some internal users, right? Then we can totally bypass proxy server. We can directly ask client to communicate with backend storage. With this, you significantly improve your performance. So we have a paper in the CIS grid last 30 years or so to describe more details. Now let's take a look at some of these numbers. So the left side is you run Swift put and get, okay? So we do a breakdown, communication, I/O, as well as some other hash sum, those kind of operations. We see that our design is able to reduce communication time by up to 3.x and 2.6x. Okay, here we are using a Malloc card. And for gate latency, similarly, we are able to reduce the gate latency by 66%. That's a big gain. Okay, so whatever I talked is about what we did in the library or in the framework. We also want to make all these solutions available. So there's one cloud called Chameleon, which led by Agang and TAG. We were also a part of that. So we make all these solutions available in their appliance market. So for example, this is the screenshot. We have here just list 2. Actually, we have 4. So we have like if you want to just run some basic SRV experiment, you can use our CentOS KVM SRV appliance. Okay, we have set up those things for you. And then if you want to run some bare metal cluster with MPI, we also have an appliance. You just do one click. You say how many nodes you want, and then I deploy. Everything automatically deploy for you. And then if you want to run SRV with KVM on bare metal nodes, then again, everything is automatically. Just do one click. And similarly for Hadoop, we also make everything available over there. Just do one click, you get any number of nodes you want, then run your application. So with this, let me conclude my talk. So overall, here, I just want to bring some information like that. If you want to run HPC on the cloud, of course, you need a lot of high-performance hardwares. But more important things, your middleware and your system, your library has to be aware of cloud environment. Okay, this is one key. Second key is, in order to get the near-native performance, the topology and the locality is very important. And then in order to support live migration, you have to do something. And all these things actually work for both MPI world as well as big data world. I believe for deep learning world, the same thing. And we actually give one concrete example, like how to run neuroscience applications in the HPC cloud. Okay, what they need, basically. How to bring the technology in this community and what they need from their community. So everything available, either in our website or in some Docker Hub or in the Chameleon cloud. So if you want to try, just go there and download them. So with this, we actually launched an above last year in SE, this year in ISC, just accepted. We are trying to discuss the future of how to build HPC cloud for different kind of applications. If some of you join ISC this year, please feel free to join. So tomorrow I will give another talk about high-performance big data analytics with RDMA over NVM and NVMe SSD. So a lot of talk has been mentioning that. So tomorrow we'll give some story what we did. With this, let me thank you. And I'm happy to take any questions.
Hi. My question is related to picking Dockers for MPI Live and not Singularity, even though your slides showed that Singularity has lower overhead. Any reason to choose one over the other, or is it just a design decision, or was it a technical reason for picking Docker over Singularity?
Yeah. So this is a good question. So the question is why Singularity can show much better performance, whether it's because of the design choice. I think the main reason is because when the first day they want to bring the Singularity to the HPC world, they keep MPI in mind. Everything is MPI friendly. Okay. For example, all the isolation settings, all those things has been enabled by default. You can directly get all the information you want from MPI layer. So that's the key. Okay, but Docker was not. So that's the main reason. For Docker, you have to do something. But Singularity, is good. The Singularity, only thing you need to be aware is that when you build the application, you may link with some version of your libraries or version of your drivers. But when you run, you need to make sure that your Singularity images also have the same environment. Okay, so for that, you can get the same performance as native, for sure. Any other questions? Okay, it's time for lunch. Thanks.